NENOMATICA, where mathematics meets YouTube excellence. Welcome to our educational math video. Today, we'll be exploring some essential laws of exponents that are crucial for solving algebraic problems correctly. Let's learn these laws through clear examples. Let's start with our first law, which is the power of a product. This law tells us what happens when we raise a product of terms to a power. When we raise a product of terms to a power, we can distribute the exponent to each factor in the product. So, the expression a raised to the power m times b raised to the power n, all raised to the power k, equals a raised to the power m, all raised to the power k, times b raised to the power n, all raised to the power k. Now, let's examine an important distinction in exponent laws, the difference between power of a power and power of an exponent. It's critical to understand that raising a power to another power is not the same as raising a base to a power of a power. When we have a to the power m, all raised to the power n, this is not equal to a raised to the power of m raised to the power n. Let's see the difference with a concrete example. When we have 10 squared, which is 100, and then raise that to the power of 3, we get 10 to the power of 6, or 1 million. This is because when we raise a power to another power, we multiply the exponents. 2 times 3 equals 6. In contrast, when we have 10 raised to the power of 2 raised to the power of 3, we first calculate 2 to the power of 3, which is 8. Then we raise 10 to that power, resulting in 10 to the power of 8, or 100 million. Therefore, 10 squared, all raised to the power of 3, is not equal to 10 raised to the power of 2 raised to the power of 3. They give completely different results. Let's examine our third property, which deals with commutativity in exponents. This property helps us understand when we can switch the order of exponents. This property tells us that when we have nested powers, the order of the exponents can be switched in certain cases. Let's understand when this works and when it doesn't. First, when we have a raised to the power m, all raised to the power n, this equals a raised to the power n, all raised to the power m. This works because in both cases we end up multiplying the exponents and multiplication is commutative. However, when we have a raised to the power of m raised to the power of n, this is not equal to a raised to the power of n raised to the power of m. This is because exponentiation itself is not commutative. Let's summarize what we've learned about exponent laws. The power of a product distributes to each factor. When we raise a product to a power, we can raise each factor to that power separately. The power of a power multiplies exponents, not raises them. When we have nested powers with parentheses, we multiply the exponents, but if we have a power without parentheses, we evaluate the exponents first. Exponentiation is not commutative in general. While we can switch the order in certain nested powers, we cannot always rearrange exponents freely. Always check the order and operation of exponents to avoid common mistakes. We'll learn how to simplify expressions and convert them to standard notation. Let's look at our first example. We want to find the result of the quantity 10 squared, cubed, and then the whole expression squared. We'll solve this step by step using the power of powers rule, which says that when raising a power to another power, we multiply the exponents. First, let's work with the innermost expression. We use the power of powers rule to simplify 10 squared cubed, which gives us 10 to the power of 2 times 3, or 10 to the 6th power. Now, we apply the same rule again to the outermost expression. 10 to the 6th power squared equals 10 to the power of 6 times 2, which gives us 10 to the 12th power. So, our final answer is 10 to the 12th power, or 1 trillion in standard notation. Let's move on to another example. Here we have 10 raised to the power of 2 cubed, and then that entire exponent is squared. Remember that when we have a tower of exponents, we must evaluate from top to bottom. First, we evaluate 2 cubed, which equals 8. Then we square this result, getting 8 squared, which is 64. Let's look at the following problem. We need to calculate 5 raised to the power of 2 to the power of 3 squared, divided by the quantity 5 to the power of 2 cubed squared. Let's start by simplifying the problem step by step. First, we need to evaluate the exponents in the first term. Starting with the innermost exponent, we have 3 squared, which equals 9. Then we have 2 to the power of 9, which gives us 512. So our first term becomes 5 raised to the power of 512. Now, let's simplify the second term. We have the quantity 5 squared, which is 25 raised to the power of 3, which gives us the quantity 25 cubed. And then we square this entire expression, which means we have 25 to the power of 3 all squared. When we have a power raised to another power, we multiply the exponents. So 25 to the power of 3, and that entire expression squared, gives us 25 to the power of 6. Now we can express 25 as 5 squared. So this gives us 5 squared to the power of 6. Applying the power of a power rule again, we multiply the exponents. So 5 squared to the power of 6 is equal to 5 to the power of 2 times 6, which is 5 to the power of 12. So our original problem has now been simplified to 5 to the power of 512 divided by 5 to the power of 12. When dividing powers with the same base, we subtract the exponents. So we have 5 to the power of 512 minus 12, which gives us 5 to the power of 500. Therefore, our final answer is 5 to the power of 500. This problem demonstrates how we can use the laws of exponents to simplify complex expressions step by step. Remember the key rules we used: the power of a power rule where we multiply exponents, and the division rule where we subtract exponents with the same base. Let's look at the problem we need to solve. We have the square root of 15 raised to the power of 2 minus square root of 2, all raised to the power of 2 plus square root of 2. First, let's apply the power of a power rule. When we have an expression raised to a power, and that entire expression is raised to another power, we multiply the exponents. So our expression becomes square root of 15 raised to the power of 2 minus square root of 2 multiplied by 2 plus square root of 2. Now, let's expand the product in the exponent. We'll multiply 2 minus square root of 2 by 2 plus square root of 2. This follows the FOIL method for multiplying binomials. First, we multiply the first terms, 2 times 2, which equals 4. Then the outer terms, 2 times square root of 2, which equals 2 square root of 2. Next, the inner terms, negative square root of 2 times 2, which equals negative 2 square root of 2. Finally, the last terms, negative square root of 2 times square root of 2, which equals negative 2, because square root of 2 squared equals 2. Now, we've simplified the exponent to 2. Our expression is now the square root of 15 squared. Since the square root of 15 squared is 15, our final answer is 15. Let's look at our example. If a equals 8 raised to the power of 3 raised to the power of 4, find a divided by 4. First, let's understand what we're being asked to calculate. We have a equals 8 raised to the power of 3 raised to the power of 4. And we need to find the value of a divided by 4. Our approach will be to first find the value of a by evaluating 8 raised to the power of 3 raised to the power of 4, and then divide the result by 4. Let's start by calculating 3 raised to the power of 4. Remember the rule of exponents. To calculate a raised to the power of b, we multiply a by itself b times. So 3 raised to the power of 4 means 3 multiplied by itself 4 times. 3 times 3 times 3 times 3 equals 81. Now we need to calculate 8 raised to the power of 81. We can simplify this by writing 8 as 2 cubed. When we have a power raised to another power, we multiply the exponents. So 2 cubed raised to the power of 81 equals 2 raised to the power of 3 times 81, which is 2 raised to the power of 243. Now, we need to divide a by 4. We can write 4 as 2 squared. When dividing exponential expressions with the same base, we subtract the exponents. So 2 raised to the power of 243 divided by 2 squared equals 2 raised to the power of 243 minus 2, which is 2 raised to the power of 241. Therefore, a divided by 4 equals 2 raised to the power of 241. Let's summarize what we've done. First, we calculated that 3 to the power of 4 equals 81. Then we found that a equals 8 raised to the power of 81, which we rewrote as 2 raised to the power of 243. Finally, we divided by 4, which is equivalent to 2 squared, giving us our final answer of 2 raised to the power of 241. Remember the key exponent rules we used. When raising a power to another power, we multiply the exponents. When dividing expressions with the same base, we subtract the exponents. These rules make working with exponents much simpler. That concludes our solution. Thanks for watching, and I hope you found this explanation helpful. In this video, we'll determine the units digit of a complex expression with nested exponentiation. We'll solve this step by step, focusing on the number theory patterns that emerge. Let's look at the following problem. Find the units digit of 5 raised to the power of 2 raised to 3 to the power of 4 multiplied by 4 raised to the power of 5 raised to 4 to the power of 3. To find the units digit, we need to evaluate each term separately, focusing only on the patterns in the units digits. Let's start with the left term. First, let's calculate the value of the exponent 2 raised to 3 to the power of 4. 3 to the power of 4 equals 81. Now, 2 raised to 81 is our exponent. For finding the units digit, we need to understand that 5 raised to any power always ends in 5. This is because 5 has a cyclicity of 1 in its units digit. So, 5 raised to 2 to the power of 81 will have a units digit of 5. Therefore, regardless of the exact value of 2 to the power of 81, the units digit of 5 raised to that power will be 5. Now let's examine the second term. 4 raised to the power of 5 raised to 4 to the power of 3. 4 to the power of 3 equals 64. 5 raised to 64 is our next exponent. We need to understand the cyclicity of 5 for large exponentiation. We already know that 5 raised to any power ends in 5. So, 5 to the 64th power will end with the digit 5. Now, we need to find the units digit of 4 raised to a power that ends in 5. Let's examine the pattern of units digits when 4 is raised to consecutive powers. 4 to the first power is 4, with units digit 4. 4 squared is 16, with units digit 6. 4 cubed is 64, with units digit 4. 4 to the fourth power is 256, with units digit 6. We observe that the units digit of powers of 4 follows a cycle of length 2, for 6, and so on. To determine the units digit of 4 raised to the power with units digit 5, we need to check if 5 is odd or even. 5 is odd. 4 odd exponents. 4 raised to that power will have a units digit of 4. So, 4 raised to the power that ends with 5 will have a units digit of 4. Now, we multiply the units digits of both terms to get our final answer. 5 times 4 equals 20, so the units digit of the entire expression is 0. To summarize, we found that the first term, 5 raised to 2 raised to 3 to the fourth, has a units digit of 5. The second term, 4 raised to 5 raised to 4 to the third, has a units digit of 4. When we multiply these, we get 20, so the units digit of our original expression is 0. Therefore, the units digit of the given expression is 0. Today we're going to learn about rational exponents. So far in our studies, we have been looking at integer exponents. Now we're going to explore rational exponents, which connect powers and roots. Let's start by understanding the definition of rational exponents. We define a raised to the power of 1 over n as follows. A equals b to the power of 1 over n if and only if a to the power of n equals b. For example, we can say that 2 equals 8 to the power of 1/3 because 2 to the power of 3 equals 8. Take a moment to think about this. Can you find the value of 27 to the power of 1/3? Rational exponents are related to radicals or roots. B to the power of 1 over n is equal to the nth root of b. This gives us another way to express roots using exponent notation. For example, the square root of 9 equals 9 to the power of 1/2, which equals 3. The cube root of 27 equals 27 to the power of 1/3, which equals 3. Let's visualize this with a few more examples. Now, let's explore rational exponents beyond the simple form of 1 over n. For any rational exponent of m over n, we can define it as follows. b to the power of m over n equals the nth root of b raised to the power of m. For instance, 8 to the power of 2/3 equals the cube root of 8 squared, which is 2 squared, which equals 4. Can you work out the value of 16 to the power of 3/4? Take a moment to try. The answer is 8. Let's see how we get this. 16 to the power of 3/4 equals the fourth root of 16 cubed. The fourth root of 16 is 2, and 2 cubed is 8. Rational exponents follow the same properties as integer exponents. For multiplication, when the bases are the same, we add the exponents. For division, When the bases are the same, we subtract the exponents. For example, 9 to the power of 1/2 times 9 to the power of 1/3 equals 9 to the power of the sum of 1/2 and 1/3, which is 9 to the power of 5/6. Rational exponents are incredibly useful in various areas of mathematics and science. They allow us to express and manipulate roots elegantly in equations. They're used in calculating compound interest, modeling population growth, and in physics equations. Let's summarize what we've learned. Rational exponents connect powers and roots. B to the power of 1 over n equals the nth root of b. B to the power of m over n equals the nth root of b raised to the power of m. Practice working with rational exponents to become more comfortable with them. Thanks for watching, and keep exploring mathematics. Let's start with our first example. We want to find the value of 25 raised to the power of 1/2. Step 1. We need to interpret what the exponent 1/2 means. A fractional exponent with a denominator of 2 represents a square root. So 25 raised to the power of 1/2 equals the square root of 25. Step 2. Now we need to calculate the square root of 25. The square root of 25 equals 5, since 5 squared equals 25. Therefore, 25 raised to the power of 1/2 equals 5. Let's continue with our second example. We want to find the value of -8 raised to the power of 1/3. Step 1. Let's interpret what the exponent 1/3 means. A fractional exponent with a denominator of 3 represents a cube root. So -8 raised to the power of 1/3 equals the cube root of -8. Step 2. Now we need to calculate the cube root of -8. The cube root of -8 equals -2, since -2 cubed equals -8. That is, -2 times -2 times -2 equals -8. Therefore, -8 raised to the power of 1/3 equals -2. Let's summarize what we've learned about fractional exponents. When we have a number raised to the power of 1 over n, it's equivalent to taking the nth root of that number. For example, x to the power of 1/2 is the square root of x, and x to the power of 1/3 is the cube root of x. This relationship helps us simplify expressions with fractional exponents. Now, it's your turn to practice. Try calculating 4 raised to the power of 1/2 and 27 raised to the power of 1/3. Remember that a(1/n) is the nth root of a. Thanks for watching. If you found this helpful, be sure to like and subscribe for more math tutorials. Let's learn how to approach these step by step using some key exponent properties. Let's look at our first example. We need to evaluate 625 raised to the power of 3/4. First, let's rewrite this expression as a power of a power. We can write 625 to the 3/4 as open parenthesis 625 to the 1/4 close parenthesis, all raised to the power of 3. Now, we need to find 625 to the power of 1/4. 625 is equal to 5 raised to the power of 4. So, 625 to the 1/4 equals 5 to the 4 times 1/4, which simplifies to 5 to the power of 1. Finally, we substitute this result back into our expression. We have open parenthesis 5, close parenthesis cubed, which equals 125. As a reminder, we can verify this result by noting that 625 to the 1/4 equals 5, which is equivalent to saying that 5 to the 4th power equals 625. Let's move on to our second example. Here, we need to evaluate open parenthesis 8 over 343 close parenthesis raised to the power of -2/3. First, let's apply the negative exponent rule. When we have a negative exponent, we can rewrite the expression by taking the reciprocal and changing the sign of the exponent. Now, to simplify this expression further, let's recognize that 343 is 7 cubed, and we can express the fraction in terms of powers. We can rewrite this expression using the power of a fraction rule, which gives us 7 cubed to the 2/3 over 8 to the 2/3. Now, let's simplify the numerator. We apply the power-to-power rule. 7 cubed raised to the 2/3 power equals 7 raised to the power of 3 times 2/3, which is 7 to the power of 2. Finally, we simplify the expression. In the numerator, 7 squared equals 49. In the denominator, 8 to the 2/3 power equals 4. So our answer is 49 over 4, or 12 1/4. Let's summarize the key strategies we've used to solve these problems with exponents and fractional powers. First, identify the base and exponent in the given expression. Second, apply the appropriate exponent rules, such as the power of a power rule, negative exponent rule, or power of a fraction rule. Third, rewrite complex bases in terms of simpler power expressions when possible. And finally, simplify the expression step by step to arrive at the final answer. With practice, you'll become more comfortable applying these strategies to solve various exponent problems. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.